Hey everybody, we're back. Welcome to Module 3 of Multilevel Modeling. And this week it's cool because we actually get to talk about multi-level modeling. We've been talking a lot about regression and getting set up with software and everything else. But now we get to dive into the real stuff, which is fun. And we're going to talk about something called the Null model, which is a really important component of multi-level modeling. So let's jump into Intro to Multilevel Modeling. I will say here, this lecture is not designed to be exhaustive. I also don't want it to be exhausting, so please don't fall asleep. But Chapter 1 of Garson provides a really nice overview of multi-level modeling and thinking about where it came from and how it works. And then Chapter 3 of Garson, this is our course textbook, shows you how to run and interpret a null model. And so again, I'm not giving you all the sort of content and conceptual stuff here. This is sort of designed to supplement that. I do think that the textbook does a really nice job of kind of unpacking and describing a lot of those elements. So give it a look. And both of those are actually available, even if you don't have your textbook yet, in PDF format on Canvas. So they're there and you can check them out. Okay, so let's talk a little bit about multi-level modeling. And you should probably know this by now, but when I write MLM, that means multi-level modeling, and that's sort of the generally accepted acronym that refers to the larger phrase of and larger class of analysis of multi-level modeling. Sometimes I also talk about MLR. So that is multiple linear regression, which we ran last module. In Module 2, you ran a multiple linear regression. MLR and MLM are very different. MLR is a regression with more than one predictor. MLM is a specific class of regression models that are designed to handle clustering. And so that's what gets us started. So MLM is an extension of regression that's used to account for observations that are clustered. In typical OLS regression, which is what we ran last week, ordinary least squares regression, we assume that each observation in our sample is independent from all the others. And what that means is that each person's unique error term, their E, if you think about the formula y equals beta 0 plus beta 1 times x plus E, the assumption is that each person's error term is uncorrelated with the others. One way to think about this, really what an error term represents, is all of the variation in an individual's outcome that is unexplained by our model. So a model might predict that I have a certain score of X or Y on a motivation scale, but my actual score is somewhat higher or lower. And that's error. That's error in the model. And what the assumption we're making is that my sort of deviation from the model is uncorrelated with everyone else in the sample. The issue is this is often violated when you are measuring things about people who are working, going to school, functioning in groups, going to schools, hospitals, clinics, businesses together. That often means that the independence assumption is violated. So in other words, my error term is actually going to be somewhat correlated with someone who shares a classroom with me or shares a home with me or shares a neighborhood with me because our context is correlated, if you think about it, right? So if I'm spending all my time in a classroom and I'm exposed to the same sort of sets of variables that another student is in terms of think about the teacher's practices and the way the school functions and the neighborhood that serves the school. All those things are variables, right? Those are all going to be correlated. And when you run an OLS regression, that assumption typically does not hold. So what does this mean in practical terms? Well, in practical terms, it can lead to 1, biased estimates and 2, biased standard errors. And those are both bad things. So when we talk about estimates, we want to get an estimate, for example, of the relationship between a student's motivation and their achievement. If that estimate is biased, it means it's going to be wrong. It's going to be too large or too small. That's not good. It might even be negative when it should be positive. Also not good. In terms of standard errors, well, if you think about the standard error, that's the sort of component that allows us to obtain a test statistic and a p-value. And remember, in statistics, we do kind of place a lot of emphasis on p-values and whether or not a finding is going to hold up given sort of repeated sampling or doing the same investigation over and over. And if you are not correctly accounting for clustering in your models, then you can also get standard errors that can be inaccurate, which can lead you to make type 1 or type 2 errors. So all these things are not things that we want in our models. So how does MLM do this? MLM actually adjusts for clustering by including an additional random variable, in this case an error term, that is shared by everyone in the same cluster. So it's basically like a regression where each person has their own unique error term, which explains what's unique to them. But then you also have a term that's shared by everyone in the same cluster. So that accounts for that shared experience within the cluster as well. And there are other additional components you can add on to MLM, but the most important sort of fundamental concept to grasp is that you are adding this additional random variability that is at the cluster, which is the thing you're trying to measure. So what does that mean? It means we now have sort of two error terms we have to wrestle with. We have a person-specific error term, which honestly we haven't paid much attention to. We kind of assume that it's non-informative in regular regression. We investigate that by checking the assumptions of regression. And then we have a cluster-specific error term, which is unique to the cluster that the person that we are looking at is found in. Okay, so here's some nice conceptual layouts, which I enjoy from Andy Field. Andy Field, I think, does a nice job of explaining kind of how this works. So we talk about MLM as functioning in levels. So level 1 generally in a multi-level model is the level at which you are measuring your outcome. In this case, for example, we may have scores from each one of the children that are listed here. And so you see in class 1, we have 8 children. We have an additional 4 children here, another 6 or 8, so on and so forth. So this is our level 1 sample. And these children are in turn nested within classrooms. So we have class 1 here, class 2, class 3, class 4, all the way to class N. You can have as many classrooms as you need, and you can have as many children as you need. These models are very robust, even to very large samples and fairly small samples. So that is sort of a classic 2-level nesting structure. So the idea here is we want to account for the fact, for example, that these first 8 children share the same classroom, and when we want to include a random variable to help us account for that, because there's some chance that the measurements from those children may be somewhat correlated just because they were in the same classroom. And the same thing for class 2, class 3, and class 4. So this is a very sort of classic 2-level conceptual breakdown of how multi-level modeling is structured. We can just add a level to this and get a little more complicated. So we know, for example, that students are nested within classrooms, but they're often also nested within the same school. So this introduces a 3rd level of random variability. So a child nested within a classroom, nested within a school, and this is what we call a 3-level model. Level 1 is the child, level 2 is the classroom, and level 3 is the school. And each one of these can introduce random variability, and we would, in this case, you guessed it, we would include a 3rd random term here to account for what school a child is actually a part of, in addition to the class that they're in within that school, and in addition to the child themselves. So there's a 3-level model there. You can also, just to sort of mix it up, I should say here before we go on to longitudinal models, there's no real limit to the number of levels that you can have. I think in R, you can actually have up to 99 unique levels. Child, class, school, region, state, country, so on and so forth. However, it's very easy to, I will say, get carried away with this level stuff. Typically, beyond 3 levels, you have to make a good case as to why those outcomes are really going to be correlated. Because when you get to these more bigger macro levels, you typically, after you've controlled for all of the sort of contextual nesting at the bottom, there's just not a whole lot of variation left to be explained. But technically, these models do extend sort of infinitely up and across if need be. Okay, so now we're going to pivot a little bit, and we're going to think about a 3-level model again. But in this case, the child has moved from level 1 to now level 2. So here, individual measurements, and these are memories. So this is a study, for example, where you're asking children to recall specific memories over time. And each one of these memories is nested within a child, and each child is nested within a class. So we have a unique term here for the moment at which the child is recalling the memory. We have a unique term for the child, and we have a unique term for the class. And actually, we could even level this up one more and look at the school, and that would be a 4-level model. This is sort of a good example of a longitudinal model. Multi-level models are very good at handling longitudinal data. Compared to something like a repeated measures ANOVA, for example, which may be something that you have experienced before, maybe in a multivariate class. Multi-level modeling is much more flexible and much more interpretable, and allows you to include lots of different covariates at different levels and do all sorts of interesting things while also looking at change over time. So that can be a real advantage as well. So that's a 3-level conceptualization of how multi-level models can work. Okay, so I'm going to pivot a little bit to from sort of a purely conceptual model to a little bit about how we actually estimate these things and how predictors are related to the outcome in a multi-level model. So Garson uses this kind of, which I think is pretty useful setup of separating level 1 variables from level 2 variables, and then using arrows to indicate the relationships between these things. So let's try to unpack this just for a second. And we'll use this as the class goes on. So if this seems a little confusing at first, again, read Garson, and also we'll keep sort of working on this, and you'll be able to apply this to your own paper by the end of the semester. So let's take an example, a very sort of basic example like a math score. And let's start there. Let's say you are interested in examining variation in child math scores, and they are measured at the student level. That is our DV, and here it's indicated by DV. Let's say we're interested in the relationship between a child's self-confidence or self-efficacy maybe and math score. This is something that's been studied a lot in EdPsych, for example, but let's just take this on as an example. Okay, so to represent this graphically, we have our level 1 covariate, which is student self-confidence, and that covariate is pointing to our outcome, which is math score. So covariate is predicting math score, and that's going to give us an estimate. We'll get a slope for that relationship, we'll get a p-value, we'll be able to figure out if those things are related. At the same time, we want to account for the fact that these children, these students, are nested in schools. And so here we have our level 2 grouping variable, which is school, and it is associated with math score because different schools might have different sort of effects on math score. And the school is also associated with the child's student self-confidence. So in other words, the school may be doing things that encourage or discourage children's level of self-confidence, and that's reflected by this arrow here. Okay, so in that way, merely the school you're in is sort of a predictor of these things and needs to be accounted for. But the cool thing about multi-level modeling is you can actually go a step further and you can say, okay, not only do I know what school these people are in, I also know how much the school is spending, for example, on its budget. So this is a school level covariate. So student level covariate, school level covariate. And we can measure the extent to which the school level measure affects math score. So does budget predict math? And we can also measure the extent to which the school level covariate impacts student self-confidence. So this is one fairly simple multi-level model with one level 1 predictor and one level 2 predictor and a grouping variable. And look at all the cool sort of interrelationships that we're able to examine just from that one particular model, which is pretty awesome. Okay, so this also maps onto sort of the 5 or 6 different types of multi-level model effects, which we're going to break down. And this comes from Garson. And I think there actually are 5. I have 6 on here, and I'm shaking my head. Oh, you can see me. I think it's supposed to be 5. Okay, so the first thing which we're going to talk about today, we're not going to run all of this at once because that's pretty overwhelming. And so we're going to break this down into some chunks, and by the end of the semester, you'll be able to do all these things, but I just want to start slow. So the first thing we're going to talk about is a null model, and that is the relationship between the level 2 grouping variable and math score. So that's telling us, is there systematic clustering or grouping by school on math score? And typically there is. Arrow 2, or model 2, I should say. Oh, it is 6. Maybe I got this wrong. Okay, so model 2, the second type of model, was what's called a conditional random intercept model. And that is what we are going to run in Module 4. So we're currently in Module 3. We're going to run a null model. Then we're going to run what are called conditional random intercept models. And that's a model where you have a student level predictor predicting a student level outcome, and you are adjusting for what school that student is in. Okay? Then we're going to kick this up one more notch. The next type of model is what's called a conditional random coefficient model, or a random slope model. And so there, in addition to arrows 1 and 2, we're bringing in arrow 3. So we're actually asking, does the slope of student self-confidence, its relationship to math, does that thing vary significantly according to what school you're in? Okay, so not only does overall, on average, does student self-confidence predict math, but to what extent does that relationship, does that slope estimate vary randomly according to what school you're in? Model 4 is what's called a random intercept regression model, and that is when we are only using school level stuff to predict individual level scores. Now, this type of model is actually fairly rare. Typically, we also know some things about the students other than their scores, their math scores. But in this case, it would be we are predicting math score based on the school budget and based on what school each student is in. So that's called a random intercept regression model. Then we get what's called a random intercept ANCOVA model. That's 1, 2, and 4. So there, basically, we're including a student level covariate. We're grouping by what cluster you're in, and we're controlling for a school level predictor. So we'll get to those. And then finally, the full-blown model is what's called a random coefficients ANCOVA model, which is all these arrows together, which includes this 5 is a 1, 2, 3, 4, and 5. So we're actually adding a random slope for self-confidence, which is arrow 3, and we are adding a cross-level interaction between budget in level 1. Now, you're probably looking at this and being like, oh my gosh, this is completely overwhelming. Don't worry about it. We're going to take this one step at a time. The big picture here is just to show you the flexibility of a multi-level model and the kinds of questions that you can ask in a multi-level framework. This gets really interesting and complicated because you're really able to break down a lot of these relationships and look at them in ways that you could never do so before. So the specific names of these things are less important than sort of being able to understand. I can include level 1 covariates. I can include higher level covariates. I can include random effects, all sorts of other things. And again, we'll practice all of this and we'll take it one step at a time. Okay, so I want to take a sort of walk through another example of this and apply it to some research on disproportionality. Because again, I'm trying to think about ways to apply this to kind of a quant-crit perspective. And disproportionality in school discipline is really an emerging and an important question in the quant-crit community, trying to understand disproportionality, particularly racial and ethnic disproportionality in school discipline. So why are kids of color being suspended at much higher rates than their sort of comparative white peers? And so multi-level modeling is actually nicely suited to answering this type of question. So instead of math score, we can look at something like suspension. Now you're probably saying, how do you model suspension as a score? And the cool thing about multi-level modeling is you don't have to. We will learn later in the semester that you can use a binary outcome, like yes or no, and model that much as you would with a logistic regression. And so here suspension is yes or no. And this could be, for example, whether or not a given student has been suspended in a year or a number of years. Remember, this could be extended to longitudinal models too. So our outcome is now suspension. And our level 1 covariate, which in our previous example was student self-confidence, again, that does not have to be a score. That can be a categorical variable. So in this case, it could be the child's identified race or ethnicity. So we could look at pretty clearly, is there a relationship between the child's race, ethnicity, and their suspension? And what that's going to mean is, are students from some racial or ethnic groups more likely or have higher odds of suspension than others? And if so, to what extent? So that's essentially what this arrow is going to tell you right here. Is there a relationship between race, ethnicity, and suspension? Okay, so that's a pretty basic question. That's been asked a lot, and the answer is yes, right? So we know that kids of color, particularly boys, male students of color, are much more likely to be suspended than their peers. But we can use MLM to extend that a little bit. We can ask a more sort of interesting and complex question beyond what maybe has been studied before. So, for example, with MLM, if we're doing MLM with a question like this, we know what schools each student is a part of. And so we're able to include not only the level 2 grouping variable, which is school, we're also able to include characteristics of the school. For example, the school percentage of free and reduced price lunch. So this is a measure of school context. So are schools, are some schools more likely to have more suspension? And what are the predictors of that? And can we control for that and sort of account for that difference when we're examining this? So any sort of characteristic of school context. This could be the number of guidance counselors in the school. This could be the number of advanced placement courses offered. I'm just throwing percentage FRPL out there as an example. And at the same time, we're adjusting for the fact with this level 2 grouping variable, we're adjusting for the fact that certain schools have more probability of suspension than others, right? Because some schools may have very much higher suspension rates in general. So we can get an estimate of the extent to which suspension really varies between different schools, which is pretty cool. So yeah, we can break this again up into the different components and start to examine it. Some of this gets pretty complicated. For example, arrow 3 here. So this is the relationship between school and race ethnicity with a random slope. So in other words, does the difference, or do the odds of being suspended for, say, a Black or Latinx student differ significantly depending on what school you're in? Answer is probably yes. And that's something we can capture with multi-level modeling. And we can sort of look at this interaction. So is there an interaction between a student's likelihood of being suspended given their race, ethnicity, and the type of school they're in, determined by lots of different variables. So lots of really cool possibilities that can be brought in. You can start to ask questions that really go beyond kind of the simple comparisons, which are pretty cool. Okay, so I encourage you, if you'd like, to try one of these. And you don't have to do all the arrows because it gets pretty crazy. But try walking through maybe 1, 2 arrows 1 and 2, maybe 1, 2, and 3. Think of an outcome that you're interested in. Think of a covariate that is measured at the same level. And then think about what a grouping variable might be and how all those things might be related. You can also think of a level 2 covariate if you'd like. So, the sort of clustering environment here, what is a covariate that might be related to these outcomes? I really encourage you to take a moment, maybe pause the video and think through that, because that is really the essence of multi-level modeling, is trying to understand, take a question, and think, what is the multi-level aspect of this? What are the characteristics of the clustering variable or the higher level variable, for example, that might really be involved here, and how does everything sort of play out? Okay, so you may have taken a moment there and have tried working through an example. That's great. It's a good way to get you rolling on your paper too and thinking about some examples. So now we're going to talk a little bit about the null model. So null means nothing. I think you might know this from math. And I have a couple cool images maybe of what nothingness looks like, or a void. There's really cool philosophy, like Sartre wrote this really cool book about nothingness. And I always think that it sounds like a metal band, nothingness, or null. And sure enough, there is a metal band called Being and Nothingness, which is pretty awesome. So this is cool. This is different. It's kind of a weird concept to think about running a model with nothing in it, but it's also important place to start when you are working with multi-level models. You have to start with this null model. All right, so first of all, what is the null model? Well, it's the first model you run anytime you think you might want to use multi-level modeling. And all we mean by null is that you are running a model without predictors. So it literally means empty. All you are including is an intercept, a person-level error term, and now we're going to get into the Greek a little bit because it's helpful. So we're going to call this epsilon. That's the person-level error term. We've always had that. And then we're going to add on a school-level random error term here that we're going to call mu. So that's the Greek letter mu. So basically we have an intercept, we have a person-level variation, and we have a cluster-level variation. And when you run a null model, it sort of breaks things down for you, and it tells you how much of the variation in your outcome is happening within cluster. So if we're talking about people within classrooms, for example, how much of that variation is happening at the person level, and how much of it is happening between cluster or at the school level. And then based on those results, you sort of decide whether or not you need to use MLM. If there isn't that much variation and you don't, then MLM is really not necessary. Now, I'm sure you're probably asking, how do I know if I have enough between cluster variation? What is that sort of statistic? And there is a helpful statistic for this. It's called the ICC, and we'll talk about that later, the interclass correlation. And there's also a estimate of the variance of the random effect at the school level, tau, this thing here, this tau. So tau is an estimate of the variance of mu. So the school level random error term is called mu, its variance is called tau, and that's the thing we really test. So is there significant variance in the school level random effect term? So the Null model here, this is just sort of pulling apart Garson's more complicated diagram and just looking at the direct thing we're looking at here. So the Null model is just looking at basically what is the relationship between the clustering variable, which in this case is school, and the outcome, which in this case is math. Okay, and so the statistic that helps us do this is the interclass correlation. And the ICC is calculated according to this formula. Basically, you take the variance of mu, which is tau, and you divide it by the sum of the variance of mu and the variance of epsilon. I know that seems pretty wordy, but in other words, what that's doing is it's telling you how much of the total variation, which is these two things, mu and epsilon, how much of the total variation is coming from the second level. So how much of the variation is happening at the cluster level versus the individual level. The higher this number it is, the more important multi-level modeling is. So here's an example. Let's say we figure out that mu is 10 and epsilon is 40. And these are estimates that we'll get with our software. You know, I'll point them right to you. So it's not, we're not hiding anything here. So the ICC then would be 10, the variance of mu, divided by 50, which is 10 plus 40. And so the ICC would be 0.2. And that means that 20% of the variation is at the cluster level, the variation in your outcome. And the remaining 80% of that variation is happening at the individual level. And the higher that ICC is, the more influential the cluster is in your model. So a good cutoff to keep in mind in social science research, an ICC greater than 0.05 is kind of evidence that you need to use MLM. So if that ICC is greater than 0.05, you probably need to use a multi-level framework. Okay, so I'm just going to show you really quickly on here how to find this in Stata. Now I'm also going to do a demo video in Stata and walk through this, but this is a good reminder to you as to where this stuff is. So here we have Stata output for our multi-level model, and we're looking at math achievement and school ID. So this is just using the high school and beyond data set. So first you get this sort of preface of results in Stata. And so you get like, some information about what estimator was used. You get some information about what are called convergence criteria. So models like this use what's called maximum likelihood, which is a little bit different estimation framework than ordinary least squares, which is what most regression is. But the details of that we'll go into a little bit later. So here we have 7,000 observations nested within 160 groups. So these are students nested within schools. We get information about the size of each group, and that's all in the preface. Then our actual estimates are down here. So the intercept, beta 0, is right here, and it's about 12.6. That's the average math score in your entire sample. So I don't remember how this math score was scaled, but the average math score, whatever that means, after accounting for the clustering of students within schools, is about 12.6. Then we have our variance of the random effect at the school level. So this is equivalent to the variance of mu. So this is the variation at the school level. It's also called tau. So the variance of the random effect at the school level is right here. And the variance at the student level is right here. And so we have the variance at the school level is equal to 9 points, and the variance at the student level is equal to 8 points. And if my window goes away, there it goes. There's the calculation of the ICC. So you take 8 and you divide it by the sum of 39 plus 8. And that equals about 0.17. So in this case, multi-level modeling is definitely justified. About 17% of the variation in math scores is occurring at the school level. All right, Team R people, this is in LME4, which is a popular multi-level package, which we're going to use. The preface of your results is right here. It includes the call, so this is the call, math achievement as a function of one means a intercept, a random intercept defined by school ID. So math achievement, random intercept, school ID. Our data here is HSB. We also get some convergence criteria and other information. We get some scaled residuals and things like that, some sort of diagnostic information. And then our beta 0, you'll notice it's the same thing as down here, so 12.63. That's the average math score after adjusting for the clustering effect of students in schools. The random variance at the school level is right here, so that's the variance of mu, again, 8.5. And the variance of the random effect at the student level is right here, indicated by residual. So the ICC, again, is 8.5 divided by 39 plus 8, which equals 0.17. Okay, so I think that's probably good for now. Just to recap, we talked a lot about sort of the conceptual setup of multi-level modeling in this lecture. We talked about 2-level models, 3-level models, longitudinal models. We also talked about the different types of variables and effects you can have in multi-level modeling. And then we talked very specifically about the Null model, which is the first model that you run to see if using a multi-level framework is justified. And we kind of unpacked that. So again, I highly recommend you read Chapter 1 of Garson. Chapter 3 of Garson as well covers the Null model and how to interpret it. This is very useful. I hope this kind of got us started on the topic, but there's lots more to say about it. But hopefully that is enough to get us going. So have a great week, and we'll talk to you soon.